Thank you, Alvin, for the kind introduction and the nice words about CERN. It's always nice to know that what we're doing is somehow visible as well in other places. So, as Alvin said, I'd like to share some experiences and a little bit of history, and then some ideas about how we've taken these, let's see, how ASICs have contributed to this Higgs boson discovery, and then how we're using the same technology for into other fields. So I'll start by explaining in layman's terms how the LHC experiment and the machine works. Now, I'm an electronics designer also, so my explanations of physics will be limited by my knowledge, but I think for a layperson it's maybe enough just to understand the basic concepts. Then I'll go through some examples of ASICs used in the experiments, how we made hybrid pixel detectors for the LHC, and how we're intending to upgrade the experiments for what's called the high luminosity running of LHC, which will start in about 2025. And then I'll switch tack and explain how we developed these chips called the Medipix and Timepix family, which had the aim of disseminating this hybrid pixel detector technology into other fields. But as you'll see later, these developments have actually kind of spun back into physics as well. So there are 3 chips I'll discuss: the Timepix chips, Medipix 3 and Timepix 3 chips, and then how we're going to see things in future, and then some conclusions. So as Alvin already pointed out, CERN is the largest particle physics research lab in the world. We have 22 European member states and 6 observers or exceeding states, of which the US is one, and then 28 non-member states who are involved in particular experiments. We're around 2,500 staff members. Those are mostly, like myself, engineers, applied physicists or technicians. So the people who actually do the physics tend to be among the user community, and those represent about 12,500 people. And they come to CERN to participate in experiments, and then they do the analysis and all those other things. The annual running budget of the organisation is about 1 billion Swiss francs, which these days is about the same as dollars. About half of that is in personnel budget, and the rest is on materials and electricity and stuff. And probably the biggest impact we've had as an organisation on your lives is that Tim Berners-Lee discovered the World Wide Web created the World Wide Web in CERN back in the 80s. So this is an image of the Geneva countryside. The airport of Geneva is there to give you a kind of idea of the scale. The accelerator complex starts here, so the offices and main buildings are here. The Swiss-French border kind of does that. So the accelerator complex is underground, crossing the border. What we do is we start off with protons here in a smaller accelerator. Those are the accelerator to higher energy into this old accelerator called the synchrotron proton, the SPS, where they're accelerated to a given energy, and then afterwards they're kicked into the Large Hadron Collider, which is in counter-rotating beams going in one direction and the other. And if you look at that in a kind of cutaway stage, this is not to scale, of course, because here near to the mountains, the depth is about 140 meters, and near to the lake, the depth is nearer to 40 meters. But in any case, the idea here is that we have these 2 counter-rotating bunches of protons. In each of the proton bunches, there are 100 billion particles, so that's quite a few. And we bring those into collision 40 million times per second, okay? Now, of those 100 billion particles which are meeting every 25 nanoseconds, only about 20 or 30 actually interact with each other. Because if you take a single proton and say scale it up to the size of a marble, the nearest proton to this one will be in San Francisco. Okay, so that's just even though we've squeezed the beams as much as we possibly could, the protons tend not to meet too often together. That being said, they create around 1,000 particles every bunch crossing, and we accelerate the protons to this huge energy of 7 TeV and 7 TeV. And in order to achieve that, you have to make the protons go fast. And this is done using a technique called RF cavities, where you basically make the protons surf on a wave, which accelerates them faster and faster to almost the speed of light. But in particular, because the protons are heavy, they have to be encouraged to turn so that they don't just go straight ahead. And to turn them, you need to have magnets. And to get the sufficient energy into those magnets without burning the entire city of Geneva, you have to cool the accelerator complex to 1.8 Kelvin, because the superconducting cables are the only way to get enough energy into the magnets to enable the to turn protons at the level of 70 eV. When the protons come into collision, they meet in the middle of the big experiments. This is an example of the ATLAS experiment. Physicist here is drawn just to give you an idea of the scale of the experiment. As Alvin said, these are big experiments. And basically what happens is that the particles collide right in the center here, and then they fly out through the detectors in different directions. And right in the middle there are tracking detectors, which are aimed at just looking to see where the particles are going. Then the green and orange detectors represent calorimetry detectors, which are trying to stop the particles to measure their energy. And those are two kinds of detector, hadronic and electromagnetic calorimeters. And then afterwards there are certain particles created called muons, which are the same as the ones we're flooded with all the time from outer space. And those actually don't stop at anything. So when these two protons, say, come into to interact with each other, a signature that you have enough energy in the collision to create new physics is that you generate muons, which will go in opposite directions. So you'll get muons coming here and here, and those huge detectors called the muon detectors, they have to simultaneously detect a muon and then tell to the detectors in the middle of the experiment that a given collision was a collision worth saving, because most of the collisions, the 40 million collisions per second, we can't possibly save to tape. We probably save about 1,000 of the 40 million which are generated. So the way the experiment works, this is a segment of the experiment, is the particles are created here. They fly through these tracking detectors. First of all, this is wrongly labeled, actually, this is a proton. The electromagnetic calorimeter stops the charged particles, and then the hadronic calorimeter stops neutral particles, and then there are the muon detectors right on the outside. Now the problem is that before the muon detectors can tell us that something interesting happened in a given bunch crossing, it takes something like a few microseconds, or maybe even 10 or 20 microseconds. So the function of the tracking detectors is to take these 25 nanosecond frames, one after the other, save them for the time it takes to get a trigger, and then only the triggered event is selected and then sent off for readout. So the whole kind of trick of the detection process is the minimization, or the limitation of what's actually sent off detector, because in most of the occasions, even if the 20 or 30 particles are interacting every 25 nanoseconds, there isn't enough energy in a collision to create new physics. And that was an engineer's explanation of how the triggering works. So looking a bit closer at the engineering, this is a segment of the ATLAS detector which I just showed, and this slide is just to show that these detectors are completely stuffed full of ASICs. Okay, so in total there are about 800,000 ASICs in the experiment, and those are connected to the tracking detector, to this is the transition radiation detector, to the calorimetry detectors, and then to the muon detectors. And similarly, if you look at the other big experiment at the LHC, which is called CMS, you see that they also have a similar kind of arrangement, slightly different detector technologies, slightly different solutions for each of the subdetectors, but you can see that in total they have about 1 million chips in the experiment, of which 700,000 are ASICs. One thing which is also to be noticed is that we probably have the largest surface area of silicon in any one place on Earth. So this tracking detector here, which is composed of 110,000 chips, is actually linked to some strip detectors, and those constitute about 200 square meters of silicon. So the big challenge of these experiments is to make ASICs which are going to withstand the radiation, because of course these collisions create a lot of radiation, and also to make sure that they all talk to each other and stay in sync at the level of 25 nanoseconds. So right in the heart of the experiments, so really right in the in this region closest to the beam pipe, we have these detectors called hybrid pixels. And a hybrid pixel detector is just a CMOS readout chip, shown here, drawn here, connected with microballs of solder to an equally segmented sensor chip. So the sensor chip is typically made of high-resistivity silicon. The thickness is about 300 microns. And as charged particles pass through the sensor, they deposit 80 electron hole pairs per micron. There's an electric field applied to the sensor which causes the charged particle, the charge deposition, to be formed into a pulse on the electronics. And it's the electronics here which I've spent the last 30 years of my life developing or studying. Now, the point here is that the close connection between the sensor and the electronics means that the charge deposited here is many thousands of electrons. Because you have this very close connection, the RMS noise which you can get on the input of these amplifiers, even if you're trying to take a frame every 25 nanoseconds, so you have to go quick, you get to RMS electron values of noise here of the level of 100 electrons, so that if you set a threshold of, say, 1,000 electrons, then you're sure to detect every particle crossing, but you won't get a noise hit. So basically you have noise-free imaging. So 100 electrons noise, 1,000 electrons threshold, and many thousands of electron signal. So the image is clean. And that was why we developed these detectors for the LHC. And I want to just go through one example of the ATLAS pixel detector here. This is a kind of engineering drawing of it. So there you can see there are 3 barrel layers. So these are around the beam pipe. And then there are some discs at the end. And all of those chips, all of these layers are equipped with the same readout chip. So the radius of these barrels from the interaction point is pretty small, and this gives you a kind of idea of the size of a single module. Now, each of the single modules making up the ATLAS detector have 16 chips bonded onto a single silicon sensor, and in total we've got about 80 million pixels in that detector. Now, this is really pitiful compared with the kind of number of pixels we have in our smartphones today, but at the level of the individual pixel, as you'll see later, there's a lot more going on than there would be, say, in your smartphone. And this is the chip. This is an old chip now. This is the FEI3 chip used in the ATLAS detector, but it shows quite nicely how a typical pixel detector chip works in a physics experiment. So this is a close-up of a double pixel here. So this is a bump bond connected to the sensor. You have a preamplifier and discriminator stage, and then basically you record the time at which the particle arrived, and then you send that information down the column to the bottom of the chip where that time tag is stored. And that time tag is stored as long as it takes for the trigger to say, hey, that event was interesting. If the trigger doesn't come, you throw away the event. If the trigger does come, you send out the image of the particle tracks. So that chip was made in quarter micron CMOS in the early 2000s. It had 160 by 18 pixels, and the pixel size is 50 by 400 microns. So I forgot to point out when I showed the image of the big experiments, but there's always a magnetic field. And the purpose of the magnetic field is to try to measure the momentum of the particles. And for that reason, you like to have in the phi direction as small a dimension as possible, and in the z direction, so in the direction of the particles, you're only limited by the number of particles per pixel which you have to detect. So as I mentioned, these things came on modules. This is a kind of blew up of one of these modules. It's got 16 of these chips here, so 8x2 chips connected to a single sensor. And then there's a Kapton foil on top, and then all of that is all the data from this is sent. The power comes in, and the data is sent out to the counting room. And this is an image of one of the technicians assembling all of these modules. So this is one of the modules I just showed there. You can see that those are being, this is the outer layer of the ATLAS pixel module. So the good news was it worked. This is an image from the ATLAS of a single event. So this is a single 25 nanosecond frame where there were 20 or 30 collisions. And what we've done here is the physicists have recreated the trajectories of each of the particles which were created during the collision, and then they've highlighted in colours here the individual collision points for the different events. Now, as I said, it's a kind of a needle in a haystack activity. So before the Higgs boson discovery was announced, there were probably a few thousand Higgs bosons detected by that time, but there had been 10 to the 15 of these events created in the meantime. So basically, the whole exercise is to try to get to the few events where you get something really new in the physics and where you can really prove that what you've discovered is coherent with the theory in that time of the Higgs. We're not stopping there. So right now we've done 2 runs of the LHC. We're stopping now for the 2-year shutdown, which is called Long Shutdown 2. And during that process, we'll be carrying out maintenance on the injector complex, and we'll be doing some work on the machine as well. We're planning a new physics run for 20 to 22, and then a further long shutdown in 23 to 25 to be prepared for the high luminosity upgrade. So in 25, when we switch on, we're going to have about 10 times more particles colliding with each other every single one of those 25 nanosecond band crossings. So the detectors have to be upgraded to cope. And I'll give you just examples here of some detectors we're preparing for LS2, so before the high luminosity upgrade, and some are preparing for LS3 to cope with the high luminosity upgrade. So I've been involved personally in this one, which is called the LHCb vertex locator. So as you saw in most of the detectors, you have this kind of barrel geometry. In the case of the LHCb detector, it's a special detector looking for beauty particles. And the way the physics works there is they've made a detector which is more kind of only unidirectional. So the particles interact, but they only really study the particles being created very close to the beam pipe and in the forward direction. So they have this geometry here, which is shown here, where you have pixel detector chips here and here, and they're kind of L-shaped. And the 2 L-shapes are kind of brought together when the particles start to collide, and they're withdrawn when the beam is being tuned. So that entire system has to work in a vacuum. And we created a new chip called the VeloPix chip. It was based on a chip I'll describe later called Timepix 3. But in total, that detector system will have 642 ASICs, or 41 million pixels. But the point here is that in all of the previous detectors which have been built so far, you always depended on this trigger in order to select certain events for studying. Because of the physics of this experiment, because the number of particles being created per second is a bit lower in this experiment, they've decided that for the first time they're going to run trigger-free. So that means that every single pixel will generate a packet of data which will be sent off detector 40 million times per second. So they're expecting about 2.9 terabits per second to be coming from this small detector in the center of LHCb. That's all based on an ASIC, which is what we do in our group. This one is called the VeloPix chip. Here we've gone away, you'll see that we've gone away from the column drain architecture to one where we're more based on superpixels. So here, instead of having individual pixels or double pixels, we've combined the pixels into superpixels to kind of get the benefit of using new design tools and techniques in order to create the logic which is needed on at the center here of these superpixels. So in the past, in fact, those first detectors I showed at LHC were done basically by hand. So even the digital part of the pix was laid out by hand. Now everything is done using libraries and all that kind of stuff. So here, the basic idea is that we'll be able to send out all of the data from a single chip over up to 4 serializer chips, which will contain provide bandwidth of 5 gigabits per second. And for that, we're using a 130 nanometer CMOS process. In fact, it's the TSMC process. Another approach has been tried in the ALICE detector. So this is a detector where, again, the event rates are lower. In fact, in this case, they're significantly lower than in the other experiments. And here, because these people are studying the collision of heavy ions, they need to have a really minimum quantity of material in the tracking detector. So in general, material is an issue, but in the case of ALICE, it's a super important issue. And for that purpose, and because they don't need to timestamp their hits to 25 nanosecond with 25 nanosecond precision, they've elected to go for a kind of monolithic active pixel detector approach. So here, the plan is to make 10 square meters of active silicon detector with pixel pitches of 28 microns. So the number of transistors per pixel is significantly lower than in the other cases. But the power density is also significantly lower, which permits to make an extremely low mass detector, which is important, as I said, for the physics. So the chip, which has been designed for that, also designed in the microelectronics group at CERN, is 15 by 30 millimeters, so it's a big chip. It's based on this concept of having, we're using the Tower Jazz 180 nanometer process, where we have the CMOS beside a collecting electrode. The depletion in the substrate isn't complete, which means that the charge collects a little bit slower than it would do in the planar detectors I described earlier. But in this case, as I said, the time tag precision isn't so important as for LHC, so we can get away with that. But the big advantage here is, of course, is that we have a detector where you have all of the electronics and the detector in a single chip, and you don't have to do bump bonding or any of that kind of thing. So these are just some numbers from the chip. It will have 130,000 pixels, and it's aiming to get a resolution of 5 microwatts per pixel, with a power down to 300 nanowatts per pixel. So for ATLAS and CMS, this is going towards the long shutdown 3. They have decided to, for once, collaborate together on a chip design, and they've made this chip, which is called the RD53 chip. And there they're aiming for pixel sizes of 50 by 50 microns. But here they're back to having to trigger or to tag every arriving particle to a precision of 25 nanoseconds. They have to deal with a pile-up of 200 particles. That means that what I described earlier of being 20 or 30 interactions per bunch crossing will now go to up to 200 interactions per bunch crossing. So this is for the high Lumi stage. And so the goal of RD53 is to basically implement an architecture in 65 nanometer, which is capable of dealing with the 3 gigahertz per centimeter square and still give efficient particle detection with good noise performance. So this is a demonstrator chip which was made last year. They're working now on the final versions for the 2 experiments. But you can see it's also a big chip. They were trying out various front ends in the process just now of choosing the appropriate front end for the experiment. The architecture, it reminds you a little bit of what I showed earlier for LHCb, but in this case, instead of having analog columns with digital columns between, they've elected to put the analog electronics in kind of islands in a digital sea. So all of this is, as you can imagine, has to be done using modern design techniques to make sure that the performance of the chip and power drops and all that kind of stuff are fully understood before going to silicon, especially since the cost of making engineering runs in 65 nanometer CMOS is not low, which is something I don't need to tell this group here. So the RD53 ASIC is in 65 nanometers. It's got these 50 micron pixels. It has to deal with a trigger rate of 1 megahertz this time. In the previous cases, that rate was 100 kilohertz. And the particle flux it has to deal with is about 3 gigahertz per centimeter square. So just to summarize then the ASICs of LHC, they were used extensively throughout the LHC experiments. I think it's fair to say the LHC experiments couldn't have worked without those. The required radiation hardness, I didn't mention this, but it has been achieved by design. So if you take an NMOS transistor, a conventional NMOS transistor, and expose it to radiation, you're going to get leakage paths between drain and source. If you make the gate annular, then you can avoid those leakage paths and essentially make the design radiation hardened. You also have to take into account that there will be single event effects, and for that you need to include triple redundancy logic to avoid those. The tracking layers in particular depend almost exclusively on ASIC design, and hybrid pixel detectors will continue to be used in regions where there's a really high density of particles. Monolithic pixels, however, start to replace hybrids in regions where there's more moderate particle fluxes, and I think it's safe to say that ASICs, and in particular hybrid and monolithic pixel detectors, will continue to play a major role as we upgrade the accelerator complex going for higher luminosities. So just a kind of summary of hybrid pixel detectors at LHC. I didn't describe all these systems because of time, but basically there were 3 large systems operating smoothly at the LHC. And what I want to switch now to is how we've taken this approach and then used it for other purposes in this Medipix 2 and Medipix 3 collaborations. So I'm going to focus down now on 3 chips which are used for those purposes. So these chips aren't designed uniquely by CERN. We tend to do everything in collaboration. So in the big experiments in ATLAS and CMS, they would have groups of designers who are maybe mostly based at CERN, but there will be people contributing blocks from various of the collaborating institutes around the world. In the case of the Medipix 2 and Medipix 3 collaborations, because this is not a baseline activity for CERN, we had to even get the resources from outside groups. So the Medipix 2 collaboration was established in 1999 with 16 members eventually, Medipix 3 in 2005, and it grew to kind of 22 members. And as you can see, those came from eventually all over the world. And we're using the same idea of hybrid pixel detectors, but in this case, instead of using only high resistivity CMOS here as the detecting medium, you can choose basically any other semiconductor detector to replace the silicon. And this is important, for example, in X-ray physics. If you have a 10 keV X-ray going into a 300 micron silicon detector, it will be detected with almost 100% efficiency. If you go up to 20K or 25 keV, which is mammography type energies, then the detection efficiency drops to something like 20% or so. And if you go to general purpose radiography, where the average energy is 60 keV, the silicon basically detects 1 in 20 of the photons. So silicon isn't an option for those kind of energies. So we tend to replace the silicon with a higher stopping power material like gallium arsenide or cadmium telluride. Another thing you can do is you can take the naked readout chip and do funny things like put a foil on top, put this thing in a gas volume, and you basically detect ionization in the gas by looking at electrons which drift down in a drift region, get amplified between the foil and the chip, and you detect that charge pulse on the chip as you would detect a charge pulse in a semiconductor detector. But basically, the concept we wanted to explore with the Medipix chips was to take the charge from the preamplifier, set one or many discriminator levels, and you can see that the noise here, the threshold here, we typically uses 600 electrons for an RMS noise of 60 electrons, and basically get noise-free imaging. So you can, to start with, we made chips which are kind of camera type chips, where you open a shutter, you count pixels, close the shutter, and read out. The second chip we made was called Timepix, where you could either do particle counting, so this shows the preamplifier output here, the discriminator output, and then what goes to the counter here. Or you can switch to a mode where you're measuring the arrival time, where you start the clock ticking or counting from when the discriminator fires until when you close the shutter, or in time over threshold, where you start the clock or you start counting clock ticks as long as you're above threshold and then stop at the end. And that gives a measure of the energy in the particle. So the Timepix chip this is designed back in the early 2000s, was in quarter micron CMOS, 256 by 256 pixels, 55 micron pitch, and either sensitive to electron collection or hole collection. This is important when you want to change the sensor material. And we set the threshold around 700 electrons, and that's a kind of image of the chip. So you see the 256 by 256 pixels here, and then there's about 2 millimeters at the bottom here, which we use for reading out the hits from the frame. And using serial readout, we can read out the entire chip in 10 milliseconds, and in parallel mode in about 300 microseconds. So I'm going to demonstrate now that chip in operation. So we have put it inside a little box here, which is connected to a USB connector, and I'll plug that into my laptop here. So this is some software developed by some colleagues in a spin-off company now in Prague called Advocam. So I'm just going to change the color scheme so we can see it easier. And then what I'm doing is I'm taking half-a-second frames here in the room, and then just displaying the counts on the image here. So that was a cosmic background. You saw a cosmic hit there. But what I brought an old watch which has got radium inside. This radium gives off high energy gammas, which when they interact with the silicon kick out Compton electrons. And so if I put that on top of the chip, you see the typical tracks of the Compton electrons as they fly through the semiconductor matrix. So the pixel sensor is 300 microns thick, the pitch is 55 microns. And when a pixel isn't being above threshold, you see nothing. And when it is above threshold, you see a color there. And that color represents the quantity of charge deposited by the electron in that pixel. So if I zoom down there, if I just stop here and zoom in, you see that there's the tracks from this electron, and the colors represent the quantity of charge being deposited there. Now, I can't travel with many radioactive sources, so I didn't bring anything else with me. But if I were to put onto the detector here a soft X-ray source, you will see the interaction of soft X-rays in the sensor material, which tends to be local, so you'll get a point basically deposited or shared between one or two pixels. Or if I put an alpha source there, which gives a lot of charge, you'll see a big blob of pixels hit because the charge spread is so high that it spreads out over many pixels. So just by using your eyes, you can see alphas, betas, and gammas. Okay, and this is this is probably the strongest feature of this technology, in the sense that you can it really gives people a kind of intuitive understanding of what radiation is, rather than this kind of vague notion of either wavy things or Geiger counters going crick, crick, crick when you see something. So just for those of you who are frequent flyers, I made these frames a few years ago. If I do the same exposure here at sea level, I did this in a hotel room in San Francisco, you see that basically there's, for 1 minute, there's very few hits in the background. If I do the same thing at 34,000 feet when I'm flying, this was done putting the chip vertically to get more long tracks, so you can see them, but if you put it horizontally, you get many shorter tracks. So when you fly, your radiation exposure is about 50 times more than you have when you're in Earth, so don't fly too much is the message. As I mentioned, the detectors are kind of intuitive for understanding radiation physics. So we were visited in CERN by this lady, Becky Parker, who's a very kind of charismatic teacher, and her then students. And she took this back to her school in the UK. They entered a UK science contest, and they proposed to make 5 Timepix chips in a kind of quad for a satellite. So they won the competition. They had a company design that for them, and then this was launched from the Baikonur station in Russia. And then this is an example of one of the students giving a lecture to his peers about the data they've seen coming from the detector. So a couple of years ago, they formed this Institute for Research in Schools in the UK, and the basic idea was that they want to try to encourage high school kids to start to do their own experiments in the classroom. Now, of course, they're not sufficiently educated to do anything really complicated, but many of the first experiments for this institute were done using the Timepix chip, and the point being that the chip is just very handy and easy to use, and it enables the kids to use it themselves in the classroom. So this is an example of one of the students giving a presentation at the CERN at School Symposium. So they hold these things every year in the UK. So they present the research to each other, and I think one of the, for me, a little bit surprising side effects of this was that using this device in the classroom has started to, or seemed to, stimulate the interest of teenage girls in the subject of physics and STEM subjects. Talking to my wife, who's an accountant, she had absolutely no interest in science when she was a teenager because she didn't understand what the point of it was. And now I think giving this kind of thing to a teenage girl and they can actually see the stuff and start to do experiments with it, maybe that starts to make more sense to them. So these are just some statistics from this institute for students going on to study engineering. So you can see that for males, there's a big difference between the schools involved in IRIS and the schools not involved in IRIS over this period of 2012 to 2015. And there's an increase in the IRIS schools and a kind of decrease actually in the non-IRIS schools. But when you look at the female students, in terms of females going on to study engineering, the numbers are still extremely low. But on the IRIS schools, they've increased by a significant factor. So that is kind of testimony to the fact that that there is in this activity something which kind of triggers girls to continue going on to study STEM subjects. So we have some of these detectors flying in the space station. This is an example of one of these plugged into a laptop beside the astronaut taking pictures here in the cupola of the space station. There are, I think, 3 of those running continuously. I think we've got 6, and I think it's going up to 10 in the next couple of weeks. If they open their shutter over the South China Sea, this time for 4 seconds, so I showed you 60 seconds earlier, this is a kind of picture of the hit they get here. Sorry, the colours have changed. 0 is white here. But what you can see is that the kind of particle to which they're exposed is different to the ones we get on Earth. So their dose is coming mostly from these highly ionizing particles, which have got a kind of characteristic track in the detector. When they're flying over Argentina, in the same 4-second interval, they get lots more hits. And that's because there's something called the South Atlantic anomaly, which is a plasma of protons which are resident over South America, and which are actually responsible for the death of many satellites. In any case, these are people from the University of Houston working with their colleagues in Prague who've been working with NASA on this. And what they've done is they've done a map plotting the trajectory of the space station and then looking at the dose rates. And you can see that as the space station flies through the South Atlantic anomaly here, the astronauts are exposed to about 5 milligrays per day. And just to normalize that, we are typically on Earth exposed to about 3 to 5 milligrays per year. So they get a significant dose as they fly through the South Atlantic anomaly. Because this worked so well, they put a couple of our chips onto the Orion rocket in 2014. They were battery operated because they wouldn't let us plug into the power of the rocket, but that gave us the advantage that we could stay alive while we went through the Van Allen belts. And this is an image of the trajectory of the Orion rocket. So in the first path around the Earth and low Earth orbit, the colours are blue, which means that there wasn't much dose recorded during that time. But then after they passed over the Cape again and they blasted off into outer space for the first time in a long time, you see that the colours start to change. So these charged particle belts are really an important contribution to dose for the flight crew. And in fact, NASA, with the view to populating the Moon and eventually Mars, have kind of baselined this approach for the future dosimetry efforts. So I should say the dosimetry effort in ATLAS, in NASA, it's not based on trying to use a detector with a tissue equivalent dose, but it's more using a standard silicon detector, trying to monitor the radiation in the environment, identify which particles are which according to the trajectory in of the particle charge deposition in the sensor, and then from that inferring the dose to the astronauts. So you can use these detectors for other things. This is an example of a 5x4 matrix of these Timepix chips imaging the excised mouse of a heart. So this is a kind of scan of the heart here. And if you look at that, the information a bit more closely, what you can see is that you start to approach the level of spatial resolution which is needed for histology. So right now, when they operate on you, they take something out of you, they send it to histology. In the histology lab, they have to do all kinds of preparations. They have to slice it up, look at it under a microscope, take pictures. Someone has to analyze it and everything else. Here, the concept is to use a microfocus X-ray source with the sample, and then use one of our detectors to reconstruct the 3D image of the tumor, whatever's been excised from the patient. The spatial resolution isn't low enough yet for histology, but it just shows a kind of a way forward maybe for histology, whereby you could maybe get an answer much more quickly by using X-rays rather than by using the visible light as the detection medium. Some colleagues in Prague have made a company who are able to look at what lies beneath paintings. So this is a painting taken from the US Embassy in Prague, and they knew that it was painted on top of another painting. So they turn it on its side, they scanned that, and what you see is that underneath that painting, there was an older painting. And the point of this technique is that by using our detectors and a microfocus X-ray source, and basically using robots to scan the painting, you can get a super high resolution image of the painting. So I can zoom in here, and zoom in here, and zoom in here, and zoom in here. So you really see the very fine detail of the painting. Now this can be used either to authenticate a painting or if you're sending your painting to the Guggenheim for display and you want to make sure you get the same one back, you can x-ray a little corner of it, and it's very difficult to reproduce at the microscopic level. So you can't fake what you can measure here at the microscopic level, basically. Something even more interesting was a recent thing. There was a collector in Europe who had a painting which was signed by Vincent. So it should be a Van Gogh painting. It looks like a Van Gogh, but no one really believed it until they started to x-ray it. And they looked and they saw something underneath the original painting, which looks a bit like a body. If you add the color x-ray information, so here, because they're using the Timepix chip, as I showed earlier, the color of the pixels indicated something about the energy of the photon being detected, and that can tell you what the material is in the painting. So they added the color x-ray information, they added a line so you could understand it and turned it around. And then by understanding the pigments used in the top layer and their energetic response to x-rays, they could subtract those from the painting and then recreate what was underneath. Okay? And what was underneath is a female nude, of course, and looking very much like the female nudes that Van Gogh was painting around about that time in Paris, just before he was alleged to have painted this new one. So this painting has gone now, this analysis has gone now to the Van Gogh Museum in Amsterdam, and everyone's kind of hoping that it will be finally authenticated. So if that is authenticated, it will be the first Van Gogh discovered for many years, and the guy who has it in his attic is going to be very happy. So there I kind of alluded to X-ray, color X-ray imaging. If you want to see through a human body, you can shine as much light as you like through the body and nothing will come out. So you have to increase the energy in the photons to come through the body. If someone's heavier, you have to increase it even further so the photons actually make it out the back. But for us, what we like to try to exploit is, so where our eyes are visible to the wavelength of the visible light, we'd like to exploit the wavelength of the light coming through the body. Okay, so the color X-ray information. And for this, in many medical setups, the rate at which the particles are arriving on the detector is very high. So it's impossible to send, like we did before, just the X-ray information off chip. So what we have to do is to do something at the level of the chip to try to make sure we can see properly the color of the X-ray being deposited. So that would give the idea, this gives the possibility of adding contrast agents, so using X-rays for functional imaging as well as for morphological imaging. But several technical challenges remain, one of which is the charge sharing in the sensor, which I'm going to explain, and then the high flux. So, as I mentioned earlier, in a silicon sensor, a soft X-ray deposits the charge locally. The charge gets collected on the pixel, but you can see that even if that charge is deposited between two pixels, it's going to spread its charge between these two guys here. And when you go to these high Z materials, which I referred to earlier, they're even worse because they have fluorescence inside. So instead of one hit, you get two hits for one incoming charge. So the question is, how can we deal with that at the level of the electronics? And so this is what we did. This is a matrix of 4 pixels with a charge shared between 4 of them. We detect the charge locally. We identify the pixel which was hit first, or hit with the most charge. Then we do charge summing in the corners, and we allocate the charge sum to the pixel which was hit. And what that does is that cleans up the dispersive process in the sensor to reproduce properly the X-ray color in the detecting pixel here. And I'll show how that works later. So this is the Medipix 3 chip. It was 130 nanometer CMOS. We can program the chip to deal with sensor pixels of 55 or 110 micron pitch, for reasons I'll explain later. And it's a frame-based continuous readout process. And just to re-emphasize this color X-ray imaging business, so these were 3 images taken in one shot of a lighter. It's maybe not the best example for a medical imaging talk. But what you can see here is that if you look at the window of photons detected at low energy, you can see that there's a good contrast here, where you have the lighter fuel and the plastic. But in the heavier parts, there's basically no contrast because all the photons get stuck there. Whereas for the higher energy photons here, you get a reasonably good contrast. Okay? But down here, you've lost the contrast because the high energy photons all fly through the soft stuff. So what you can do with color X-ray imaging is combine those 3 images into one, whereby you can maintain the contrast in the in the lowly absorbing parts of the lighter or the body, and then also in the highly absorbing parts. Okay, so you can basically get more information from the same dose given to this lighter. Okay. I'll skip these because I'm a little bit late. So we have colleagues in New Zealand who started studying this using the small animals. They made a small animal X-ray scanner. This is their scan of a mouse, and whereby there you can see that they've been able to, by using the accessing the color spectroscopic information, they'd injected gold, gadolinium, and iodine, which are 3 elements used in medical imaging. And by looking at the colors, you can distinguish well one organ from the other because they have different absorptions for these different materials. But this summer, they finally published some examples of this imaging being applied to the a human body. So when you go for an X-ray, the first thing the radiologist says is take off your watch and all metal objects. And the reason for that is because the X-rays are deviated by the metals and tend to be scattered, and it screws up the image completely. If you have access to the color information, you can overcome this problem of beam hardening in the image. So in this case, the professor in New Zealand, he left his watch on just to demonstrate it. And what you can see is that because bone absorbs X-ray energies with a different coefficients than, say, regular flesh or fat, you can see one thing from the other. So you get, by having access to the color X-ray information, you get a more precise image of the body, and in particular you can distinguish one material from the other. And this is maybe shown a bit better here. This is a scan through his ankle. So there we're kind of stripping away, cutting away through his ankle, and if I stop that somewhere in the middle here, there what you can see is the fine structure of the bones. This is an old guy, so his bones are getting a bit porous. You can see the yellow stuff here. This is fat, and the red stuff is regular flesh. So basically, the group in New Zealand are radiologists mostly and some physicists, and they kind of identified this as a promising topic, and they've started to study it. Every couple of years at CERN, I organise something called the Workshop in Medical Applications of Spectroscopic X-ray Detectors. This is a thing by invitation only. We try to limit it to about 100 invited participants because we're trying to really have a discussion between the people there. The big medical imaging companies all send big groups to the meeting, as do the big medical imaging faculties, let's say in Johns Hopkins, Mayo Clinic, etc. So there, of course, the big medical imaging companies, when we started this, so this basically started from a post-conference dinner drinks with a couple of guys from Philips and Siemens and myself. And they were interested in spectroscopic imaging. I was interested in it. No one really believed it would work. And we started this in 2011, and we've reconvened every couple of years since then. And I think the big companies will never use a solution developed by CERN, but they'll use their own internal solutions. But what we've done here is try to just act as a motor for the development of this imaging modality. So our most recent chip is called Timepix 3. It's also in 130 nanometer CMOS. It also has the usual 256 by 256 micron, 256 by 256 pixels, 55 micron pixel pitch. But in this case, instead of using a frame-based readout, we use a data-driven readout. So because the pixels only fire when they're hit and they shut up the rest of the time, you can make an architecture whereby when the pixel gets hit, he spontaneously senses information down the column and off. So this is the same approach as we used for this VeloPix thing I mentioned earlier. But in this case, for the Timepix chip, we record the particle arrival time with a precision of 1.6 nanoseconds, and we send off energy and arrival time information at the same time. So if I look at a 300 micron thick sensor, in the past, what you detect on the pixel electronics here is a projection of the charge deposited by the particle in the sensor. And you couldn't distinguish a particle like that from one like this because you didn't see the arrival time of the charge. But if you can see this arrival time of the charge, then you can well distinguish the direction of the charge deposition in the sensor. And then it's quite nice, you can actually see effects like delta electrons, which are kicked out by the passing particle. We've used this in an experiment for antimatter research at CERN, so we're going kind of back into physics at some level. It's like a kind of electronic bubble chamber, if you like, and I'll go over this quickly, but basically they made a movie of an experiment where they were firing antiparticles at one of our detectors. In the beginning, they only had some kind of background crap, which didn't give much information. But then around 700 nanoseconds, you start to see these star-shaped events. And those star-shaped events are the annihilations of the antiparticles with particles inside the silicon sensor, and then the generation of the debris particles. So it was just an example to show that this kind of chip, while being very useful for all kinds of other things, is also useful in the physics environment. So in a more or less hour of a lecture, I can't go into all of the applications to which the chips have been put, but I just made a list here of some of the imaging domains where our chips are used. And in particular, back at CERN in physics, and this I always show to my management, we've actually used it heavily also now in various experiments in fundamental particle physics. We have a number of licensees, two of which are established companies, in particular Panalytical have been a partner since 2000 or so with us, and they've sold many thousands of our devices. But what's maybe more important from the perspective of our lab and our governments is that we've created a number of startup companies have been created in our member states. So this is nice for promoting employment in Europe. So what's next? Well, we would like to, what I've shown so far, you've always had a sensor with a chip underneath and then wire bonds down to some kind of surface. And the big 4x5 matrix there, they obtain by kind of tilting the sensor and then wire bonding underneath the next sensor. It's always a bit cumbersome. But what we'd like to do is look at the use of through silicon vias to make a 4-side buttable tile. This we've done with Medipix 3. So this is the Medipix 3 chip. This is the pixel matrix here, where we're going to bump bond our sensor afterwards. And this is after bump bond and TSV processing, whereby the edge of the chip is just here, and all of the I/O, this is the back of the same chip here, all of the I/O is taken out from one column here and then spread over the back of the sensor. So that we've done wafer maps to make sure the yield was reasonable. We lost dye around the edge, but we think we know how to deal with that. So that gave us the confidence by looking at statistics of the TSV processing to go on and make chips now which are really designed to be 4-side buttable. And that's a complicated thing. So we follow our own Moore's law. We're like 20 years behind you guys, but okay, that's how it is in research. So we'll try to make two chips, a Medipix 4 chip, which will try to answer the medical application by counting faster and tiling an area seamlessly, and the Timepix 4 chip, which we'll use, we will try to time tag the arrivals of the particles to a much greater precision. These are the specs of the Timepix 4 compared with Medipix 4. So basically, we're making things bigger. So our single die will be about 7 centimeters square now in future, and we'll be able to deal with about 800 gigahits per centimeter square per second, so about a factor 8 or 10 greater than before. And the Medipix 3 chip, there again, the die size will be significantly increased, and the number of particle counts per second will be significantly increased. So in Medipix 4, we have 14 collaborating institutes for now. We're adding a few in the next couple of months, I hope. So just to conclude, hybrid pixel detectors were developed principally for the tracking detector of the LHC, and made, I think, important contribution to the Higgs discovery, because we helped disentangle these very complicated events. Hybrid and monolithic pixels will continue to contribute to tracking detectors going forward. Now, what we'd obviously like to get to in future is to stack our wafers. So this we haven't managed to obtain yet, but we're looking for solutions to that in future. The Medipix 3 and 2 and 4 collaborations have taken the technology to other fields. The Timepix chips have been detecting background in classrooms and in space. Color X-ray imaging in Medipix 3 has, we think, significant potential for medical diagnostic imaging. And I think the Timepix 3 chip is opening new possibilities for single-layer tracking and a number of other applications in physics, which we discussed before the start of the talk. And spin-off activities go back to physics, and this is a message from my management in case of watching. So thank you for your attention.